Hi, AP Statistics. So I know you guys have a lot of questions, and I don't have a lot of answers at this point. We're going to be out of school for a while, and I do not know if the AP exams are still on or they're canceled, or you're going to be able to take them at a different date. We don't really have that information yet. So as soon as I do know that, I will let you guys know. For right now, we're going to try to continue our kind of regular schedule of content like Monday, Wednesday, Friday. So I'm going to assign you guys some homework today that would hopefully be due on Friday. Friday, my plan, at least at this point, is to do a Zoom live call where you can jump on and ask me questions so that I can solve problems or answer questions in a chat box that you guys can submit questions and at least have some sort of interaction with you guys. We should be able to record the live call so that I can also share that with you if you're unable to actually like log in at the moment that I'm live. But I got to figure that out. And then I'll share the link with you ahead of time in the Google Classroom. So be checking the Google Classroom and my website for updated information, assignments, and some things like that. So the goal for this, I don't really know how long we're going to be out officially yet. I'm thinking it's quite some time. We will finish this chapter. We will also try to do chapter 14 as well. We may do some assessments through the AP classroom. Um, but yes, I'm just trying to figure it all out right now. So that's just how we're going to fly. But feel free to reach out to me if you have specific questions that I haven't answered. So today, this note is going to be some more content about two sample mean procedures. So, I think I told you guys before we left that this chapter is really, really important. I mean, and I'm assuming that we're still taking the AP exam. But this chapter is something that really has a lot of content on the AP exam. So it's best if you can follow along. I don't have a graphing calculator that I can show you what I'm doing. So I'm going to try to explain the steps as much as I can, even writing stuff on the side. If we need to, I have a picture of a calculator that I can pull up, but it's definitely going to be best if you actually work this through with me while we're doing the notes. So, all right. So, well, let's go ahead and get started with this. A new program of imagery training is used to improve the performance of basketball players shooting free throw shots. The first group did an hour imagery practice and then shot 30 free throw basket shots with the number of shots made recorded. A second group received no special practice and also had shot 30 free throw basket shots. The data are below. Did the imagery training make a difference? And then use alpha 0.05. So the one thing to start off with, and you also probably saw that in the means worksheet number 1 that you guys had for homework, you're going to be choosing between whether these are two independent samples or if they are matched. And so for this, they happen to have the same sample size. It means the two groups had the same number of people in it. But are they linked? Are these like the same people? Like just these first two shots, like one made 15 and one made 5, are those linked in any way? And the answer is no, they're not linked. They just happen to have the same number. There's 6 people in each group, but the first record is just for that first person who shot that in group 1 and the first person who shot in group 2. They're not linked. So these are going to be two independent samples. So over here, I'm going to define let mu1 equal the mean number of shots made by group 1 with which had the imagery training. and let mu2 equal the mean number of shots made for group 2, which had no training. Okay, so it is important to define your variables here. And so our null is that they're going to be the same. So you can write this as mu1 equals mu2, or if you would rather write it as mu1 minus mu2 equals 0. That's saying the same thing. You only have to write this one way. So just write it once, but whichever one makes sense to you. And the alternative hypothesis we're looking for, does it make a difference? I mean, really, you would think that they would want to improve the number of shots made, but a difference itself would just be not equal to. So you can write this however you want, either one. Okay, and then we are going to write out our conditions. Well, first we can say that these are going to be two independent samples. Of basketball player shots. Oops. Okay, so they shouldn't influence each other in any way in that. And then we are also going to say, whoa, that's way too far, sorry. Simple random sample. It doesn't really say, I don't think. So we're just assuming these two groups of basketball players. I cannot spell right now. Are simple random samples. The other thing we need to check for is approximately normal. And so for this, we have raw data. So you're going to have to stick both lists in your calculator. So we can go ahead and do that. And then we're going to either do box plots or normal probability plots for each. So you're actually going to have two plots drawn on your paper. So we can label them like group 1 shots made. That's probably too small of a graph, but oh well. And group 2. So I'm doing normal probability plots. You can do whatever it is that you want to do. Just putting a scale on here. Okay, so once we have these in the list, we're going to do normal probability plots, graph it. So, I mean, I'll just put mine on here. I'm sure you all know how to do this at this point. But the difference is that you're just doing it twice. You're doing it for, not for the difference, but for each plot because they're independent. I think mine's a little bit off, but okay. So you should get something that looks relatively linear. I don't remember off the top of my head what the box plots look like. Hopefully, I'm guessing group 1 might be a little bit off, but group 2 probably looks like it would have an approximately normal box plot. But so either whatever graph you do. And what we're going to say here is since both normal probability plots appear linear, assume both the distributions of shots made are approximately normal. Okay, so now we're going to do our test statistic. So this is, oh, let's put that over here. We're doing a 2 sample and we're doing a t-test. That's all we do with the 2 sample information. We just have this sample standard deviation. That's how you check. That's what we've been doing on this whole time. So our test statistic, I'm going to write the formula again just so we can all make sure we know it. X bar 1 minus X bar 2 divided by square root standard deviation 1 squared over n plus standard deviation 2 squared over n. Okay, so this stuff, you are going to get all of this from the calculator since you entered all this information in there by doing one variable stats. Okay, so that's where all this is going to come from. You can tell though by the numbers, hopefully, like this one, the first group looks like, you know, the numbers are in the 20s, whereas the other ones it's in like, I don't know, single digits and in the teens. So you should be able to tell that just there does look like there's going to be somewhat of a difference. Okay, so one variable stats list 1, one variable stats list 2, and we're going to get 21.67 minus 12.33 for the 2 means. And the standard deviation of the first one, divide by, and our sample size is 6 for both of them. And then the standard deviation of the other divided by 6. Okay, so then plug all that into your calculator to get your test statistic. I still recommend doing that all at once using parentheses around the top. But go ahead and do whatever you're going to do. Or just wait for me to tell you the answer, which is probably what most of you are going to do, but whatever. 2.839 is what you should get. Okay, so our p-value now, we are doing a 2-sided test, so probability that my t is greater than the absolute value of 2.839, it's going to be 2 times t CDF. Again, we're doing a 2-sided test, so we're at 2.839 and going to that tail, as well as negative 2.839 and going that direction. Okay, so we're doing both sides. So this doesn't matter, you're just doing one of the tails. So I'm going to do 2.839 to positive infinity. And then what are the degrees of freedom here? This is the special case. So if you go back in your notes like a page I highlighted, hopefully you at least underlined, when the sample sizes are the same, there's a special case. So here they're the same, so you're going to add them together. So 6 plus 6 and then minus 2. So here your degrees of freedom are going to be 10. Okay, if they're different sizes, you take the smaller one minus 1. But since these both have the same sample size, watch out for that. Degrees of freedom are 10. So calculate your test statistic. Don't forget to multiply it by 2. And so we should have 0.0176 or something close to that, depending on how many decimal places you use. If you use slightly less decimal places, oops, sorry. Okay, so for this one, our alpha level is a 0.05. So our p-value is smaller than alpha, so we're going to reject. So since our p-value is less than or equal to alpha 0.05, we're going to reject the null. So there is sufficient evidence to suggest that the mean number, don't forget mean, shots made after imagery training differs from the mean number of shots made without imagery training. All right. So on this, let me just scroll down a little bit. We're also going to do a confidence interval for the same data, just while we're talking about it. We have the same conditions: simple random sample, independence, and normal. So a lot of times these are a follow-up, like part A, do a confidence interval, part B, do a test. So it's very similar to our structure that we've been doing. We're subtracting the sample means here, plus or minus. T star is the same T star that we've always been calculating, just watch your degrees of freedom. And then this is the standard deviation for the two sample situation. Okay. Sorry. So we're going to calculate and interpret a confidence interval. The conditions are the same, so we don't have to check them again. We've already checked them. Done. So we can just jump to the confidence interval part. So I'm going to write that down here: x bar 1 minus x bar 2 plus or minus t star standard deviation 1 squared over n1 plus standard deviation 2 squared over n2. Okay, just so we have it. We're going to plug in our stuff, which we've already calculated above a bit. So we should have 21.67 minus 12.33 plus or minus, we're going to find t star, and then the rest of this information we already have. So 5.05 squared over 6 and 6.225 squared over 6. That's not the right number. What is it? 28. No, it's a 27. Sorry. Sorry, it's a little messy. It's hard to erase this thing. Okay, so T star, same way we've calculated this. 97% confident. So that means our tail is 0.005. Our degrees of freedom, again, we have the same sample size. So we're going to do 6 plus 6 minus 2. So we've got 10. And then you're going to find t star. So either you look it up on the table like you normally do, or you can do inverse t in your calculator. However you're going to find that. This should be 3.169. Okay, so you're going to add and subtract, or find the difference there. So this should be 9.34 plus or minus. Simplify that whole right side and get the margin of error. So you get 10.425, and then add and subtract that. And with these difference problems, what you really want to notice is where 0 is. So for this, you notice that 0 is in this confidence interval. So why did we not get the same answer to part A? Part A we rejected. This part we're finding that 0 is in the confidence interval, which is saying there's not that much of a difference. What is the difference in these problems? The first one, the one above, was at alpha level 0.05. Whereas here, we're doing a 99% confidence interval, which would correspond with an alpha of 0.01. And if you look back up, the p-value, we would have failed to reject using alpha 0.01. So we can see 0 lies in this confidence interval, which is what we would also say that there's not that much of a significant difference at 99%. So even if it's not, we're higher on the positive side than on the negative, but we're still estimating that the difference is close to 0. So that's just all we're saying. So we can say I am 99% confident that the true mean difference in shots made with imagery training and without imagery training is between negative 1.08 and 19.77. All right, I wanted to show you a couple other things as I kind of go to the next page. Using technology. So this comes in, I'm going to show you how you can use technology. However, once I show students this, their work goes downhill so quickly. So be very, very careful with how you use this. Use this as a tool, not as a crutch to be able to solve every single problem. So the problem that we just did, we have the data in the lists, okay? So I wrote out the commands for us to go and see. And this is also going to come up with our calculated degrees of freedom. So this is the official formula here that the calculator is going to do for us, which you don't need to know it in any way, shape, or form. However, just notice that it's complicated. It's a calculation, and so we're going to get degrees of freedom that are exact and come out as decimal accuracy, okay? So you already have the data in your list. So we are going to go to stat, and you're going to go over to test. Okay, so here are your commands right here. Stat, go over to tests, and actually all the tests are there that we've ever done, confidence intervals and tests. So again, use this with caution. I don't show you this until now because I usually don't actually want you to use this. When I'm looking at your work, I should not be able to tell the difference of whether you use the calculator or you did this all by hand. So, okay. So we're doing a 2 sample t-test. So hit enter. And you can either choose stats or data. At the top, it's going to have either one. So the stats would be that you have just already the summary statistics. You can enter the mean for one, the standard deviation, and the sample size for one. Do the same thing for the other one. Or you can choose data, and that's like for this case where we have our data is already in list 1 and list 2. So you actually want to choose data since we already have our data in L1 and L2. So you're going to choose list 1 is L1, list 2 is L2. Frequency you want to keep as 1. That just means you're counting each value in the list as one value. And then you get down to where you have mu1, you can either choose a not equal to test. So this is the alternative. You can choose not equal to, you can choose less than mu2, or you can choose greater than. So it just depends on what type of test you're doing. And you just move the cursor and hit enter so those are highlighted. The one we did was the not equal to test, so we want that one highlighted. For pooled, for pooled, you never want to choose that. Always choose no for everything we do. What that's going to do is it's going to pool the standard deviation so that you're just using one standard deviation. We're fine having 2 different values. So you hit no and then hit calculate. Okay, so when you do that, you should come up with all the information that we just calculated. So test statistic, the p-value. It's going to find the degrees of freedom for you. So this one, if you did this correctly, your calculator degrees of freedom should be 9.556. We estimated our degrees of freedom with our approximation as 10. So it's pretty close. You can anytime use either one. You can use our approximation or the value that you get from the calculator. So even if you're showing all your work by hand, but you've used the calculator, you can always use either one. Okay. When we have when we have the sample size is the same, these values are going to be pretty similar. When we have two samples that do not have the same value, we use the estimate of the smaller one minus one. This calculation will most likely be quite different than the value that we get using the smallest one minus one, and that's okay. So it may change your p-value if you're comparing your answers to like your friend, but I have both answers, so it's fine. It only changes it in a very minute way. Also, the AP exam is written so that the multiple choice, no matter which one you use, you would select the correct answer. Okay. So that is some good information for you there. Oh, also in the calculator, it also will give you your summary statistics. So the mean of data set 1, mean of data set 2, standard deviations, and your n. So you can always use that and just stick right there to get all of your summary statistics too. Okay. I'm going to skip over this next example. It's very similar to what we just did. However, if you want some more practice with this, I can post the answer to this on my website as well, so you can definitely double check your answers for this. So we're going to jump down. I don't know what happened to my... Sorry, my screen got stuck. So we're just going to jump and fill in some of these little fill in the blanks for the two sample procedures about means. So remember the definition of robust. We've seen that a few times. An inference procedure is called robust if the probability calculations involved remain fairly accurate when a condition for use of the procedure is violated. So the two sample procedures are more robust than one sample t methods when the sizes of the two samples are equal and the two populations being compared have distributions with similar shapes. Probability values from the t-table are quite accurate for a broad range of distributions, even for the sample sizes as small as 5. So we can get away with more basically of it not being perfectly normal and still get fairly accurate results. That's what this is saying. When the two populations have different shapes, larger samples are needed. And this is like a good rule. I mean, most of the problems we're going to give you are like this, where you want your sample sizes to be at least 5. If you get to plan the two sample study, it's ideal to choose equal sample sizes. So that's only if you were going to conduct the experiment, that would be the ideal thing to do. But if you don't have equal, it's fine. But if the sample sizes are the same, then option 2 for finding the degrees of freedom is really accurate. So taking n1 plus n2 minus 2. And so the two sample procedures are most robust against non-normality when the sample sizes are the same. So again, if you're using the same sample size for both groups, you can get away with things that aren't perfectly normal. So don't use pooled two sample procedures. This applies to the calculator. We are never going to use that. Unpooled is what we use where the two sample procedures have different variances. They don't have to be the same. Pooled assumes that both populations have to have the same variance, which is not what we are normally assuming. Okay. All right. So hopefully that helps clarify some of the two sample mean procedures. Your guys' homework is going to be mean worksheet number 2. I'm going to put that in my website. It's probably already up there now. you can just do this on a piece of paper. You do not have to necessarily print out the worksheet. If you have a printer, awesome. If not, feel free to do it on a piece of notebook paper, a piece of white blank paper from your computer, whatever. However you get this done, that would be great. And my goal is Friday to have a Zoom call that you can tune into live to answer questions. Well, for you guys to ask questions of me, and I will try to answer questions just like this where you can see me write out the problems, and I'll be able to share my screen with you. So that is the plan. If you need to get a hold of me, feel free to email me. Again, we are working to do what we can right now. As soon as I have information, I will pass it along to you guys. But most likely, it's looking like our schools are going to be closed for quite some time. Again, as soon as I have information about the AP exam, whether it's canceled, whether you can still take the tests and postpone them, this has never happened before, so we're just kind of doing the best we can. So I hope you guys are doing well. Stay healthy, stay home, rest, and enjoy some downtime. All right, I'll talk with you guys soon.